Partial discharge PD represents a localized electrical breakdown phenomenon that occurs in insulation systems under high voltage stress without completely bridging the insulation. This phenomenon serves as one of the earliest and most evident indicators of insulation defects and deterioration, making it a critical parameter for condition monitoring of high voltage equipment. The significance of PD monitoring lies in its predictive capability. PD activity is often present well in advance of insulation failure, providing asset managers with valuable time to evaluate the condition and make informed strategic decisions regarding timely repair or replacement before unexpected outages occur. The physics of PD involves the generation of short-duration electrical pulses that propagate through the equipment's insulation system, creating measurable electrical, electromagnetic, and acoustic signatures. These signatures vary depending on the type of defect, the insulation medium, and the equipment geometry. In power transformers, PD can originate from various sources including voids in solid insulation, gas bubbles in oil, floating components, surface tracking, and contamination. The evolution of PD typically follows a pattern of increasing intensity and frequency as the insulation condition deteriorates, eventually leading to complete breakdown if left unaddressed. Understanding the nature and characteristics of PD is fundamental to implementing effective monitoring strategies and interpreting measurement results accurately. Modern PD monitoring systems leverage multiple detection techniques to provide comprehensive assessment of equipment condition, with each technique offering unique advantages and limitations depending on the application environment and monitoring objectives. Conventional electrical PD measurements, standardized by IEC 60270 and IEC 600763, have been practiced since the 1960s and remain the gold standard for factory acceptance testing and laboratory assessments. These methods measure apparent charge in picocoulombs PC using the bushing C1 capacitance as a coupling capacitor to decouple high-frequency PD pulses from both internal and external sources. For bushings without a capacitive tap, an external coupling capacitance is connected in parallel with the bushing, and the PD measurement system is connected to the sensors via coaxial cables. The conventional method allows precise calibration but requires a sufficiently high signal-to-noise ratio SNR in the measurement circuit to easily resolve the PD signal. The primary advantages of conventional PD measurements include their ability to be precisely calibrated against known references, providing standardized results that can be compared across different laboratories and against pass-fail criteria, typically 500 PC for factory acceptance. Additionally, phase result PD patterns are widely available for different discharge defects and high-voltage components, enabling more accurate diagnosis of specific fault types. However, conventional methods face significant limitations in field applications, particularly their sensitivity to electrical noise from external sources such as inadequate corona shielding of line terminals, bad or loose connections, PD from other interconnected high-voltage systems, or arcing from transmission lines. While factory testing is performed inside Faraday cage-style shielded laboratories free from PD connections and terminations, this approach is impractical for in-service transformers exposed to various noise sources. Several established procedures are available to suppress these interferences for on-site measurements, but they add complexity to the testing process and may not be fully effective in all environments. Ultra-high-frequency UHF PD measurements have emerged as a valuable alternative for online monitoring, particularly in noisy environments where conventional methods struggle. UHF detection operates on the principle that PD generates fast rise-time electrical impulses that radiate electromagnetic waves in the frequency range of 300 MHz to 3000 MHz. These measurements utilize UHF antennas inserted into the transformer tank through oil sampling valves, with the metal surface of the transformer tank acting as a natural Faraday cage to filter out electrical interferences from outside. The high-voltage bushing C1 capacitance further enhances this filtering effect by acting as a low-pass filter to reduce electrical interferences from outside the tank. Three main types of UHF probes are commonly used: oil drain valve probes designed for straight opening valves at least 1.5 inches in diameter, hatch cover type probes installed through dielectric windows on the tank wall, and flange type sensors fitted around the lower shed of high-voltage bushings. Each type has specific installation requirements and limitations. For example, oil drain valve probes require careful placement to avoid compromising transformer safety, while hatch cover type probes require transformer outage and oil drainage for installation. The sensitivity of UHF PD measurements is influenced by several factors, including the antenna's structural design and materials, the depth of the probe head inside the tank wall, the distance between the PD source and antenna, and the presence of obstacles between them. Empirical studies have shown signal attenuation varies between 2.0 dB by 50% loss when obstacles exist. Despite their advantages in noisy environments, UHF measurements have significant limitations. They cannot be calibrated in terms of apparent picocoulombs as per IEEE and IEC standards, making it difficult to relate field measurements to factory reference values. They cannot uniquely identify which phase windings are affected, and the required equipment is typically more expensive than conventional PD detection systems due to the higher frequency components needed. Ultrasonic acoustic PD measurements provide a complementary approach to electrical methods by detecting the acoustic emissions generated by active PD sources in oil-filled transformers. These acoustic signals propagate through the intervening material to reach the transformer tank wall, where sensors placed at different locations detect them at varying times based on their distance from the source. The relationship between distance, time, and acoustic wave speed forms the basis for PD source location using acoustic methods. Two main categories of acoustic location systems exist: all acoustic systems that use only ultrasonic transducers to detect and locate PD sources without requiring voltage or current readings, and acoustic systems with an electrical PD trigger that pair acoustic sensors with electrical detection devices to provide a time reference for the PD event. The signal sensitivity of acoustic monitoring varies significantly based on the specific system and installation, with generally detectable sources including PD outside windings, arcing or tracking of bushing surfaces in oil, PD inside tap changers, and very high-intensity discharges within windings. However, acoustic detection faces challenges with discharges within windings, inside HV bushings, and signals produced by gas bubbles, which are typically difficult to detect. Weather conditions: rain, snow, sleet, hail, lightning strikes, and mechanical disturbances, core magnetostriction, pumped liquid noise, loose shielding connections, fan noise also interfere with measurements, and sensor placement significantly affects accuracy. The primary advantages of acoustic detection include immunity to electromagnetic interference and the ability to locate PD activity, though acoustic signals suffer from high attenuation, making detection of low-intensity PD difficult. When comparing all three techniques, conventional electrical methods offer precise calibration and standardized results but struggle with noise in field applications. UHF methods excel in noisy environments and are suitable for online monitoring but lack calibration standards and phase identification. And acoustic methods provide excellent location capability and EMI immunity but face challenges with signal attenuation and environmental interference. The choice of measurement technique ultimately depends on the specific application, environment, and monitoring objectives, with many organizations employing a combination of methods to leverage their respective strengths.